So yeah, anyway, so we'll spend a little time working on the lab at the end of class. But before we do, we need to do part two of 4 of stoichiometry, and that is what happens when you have 2 reactants that battle it out to be the limiting reactant. Now, sometimes exercises are easy on you and they say this chemical with this chemical and this one's excess and this one's limiting. Not always. Okay? So maybe we should first talk about what it means for something to be limiting. What does it mean when something is a limiting reactant?
There's not enough of it.
Okay, there's not enough of it? What else?
It'll run out faster.
It's going to run out. Good. What else?
There's only so much.
There's only so much. So yeah, so the limiting reactant is going to be the one that runs out first. There's only so much, and it's going to be the one that determines how much product we make. It's kind of like if we were having a bake-off, and you had your ingredients, and I had my ingredients, and we both followed the recipe perfectly, but you made 24 cookies, and I only made 18 cookies. You're like, hey, one of my ingredients was limiting. So the limiting reactant is the one that determines how much you make. Make sense? Now, when you have 2 reactants and it doesn't explicitly tell you this one's excess, this one's limiting, what you need to do is make 2 T-charts. Yep. Okay, so without any questions before we jump right in? All right. So consider this exercise. How much water can be produced when 12 grams of oxygen and 5 grams of hydrogen react? 12 grams of oxygen, 5 grams of hydrogen. Which one on the surface looks like it might be the limiting reactant? Yeah, it looks like hydrogen because there's only 5 grams. But do grams and grams react? No. What reacts?
Grams and
Moles and moles react. So the grams doesn't tell us anything about what might be limiting. So to do it, wake up, Maggie. Wake up, have some coffee. We need to make 2 T-charts. The first T-chart will be with our first reactant, and the second T-chart will be with our second reactant. So we make 2 T-charts. Now you can do this making one whole T-chart and another whole T-chart, or you can do like I'm doing and making the 2 T-charts simultaneously. That means at the same time.
Yeah.
I prefer it this way, but you can do it whatever way you want. So the first T-chart starts with our first reactant, which is 12 grams of O2. And our second T-chart starts with our second reactant, 5 grams of H2.
Wait, why
Yes.
do you do 2 different ones instead of like trying to get the 12 grams to the 2 to 5 grams?
Because we're not comparing them versus each other, we're comparing them versus the product. So we want to know if 12 grams of oxygen was limiting, how much product would we make? If 5 grams of hydrogen was limiting, how much product would we make?
So we're figuring out which one's limiting.
Yep.
Okay.
So, and we're both going to go to grams of H2. That is our goal. So our goal with both T-charts is to find out how many grams of water we could make. The one that makes the least is our limiting reactant. So once we understand that idea, that you make 2 T-charts, one for each reactant, then it just becomes a mass-mass stoichiometry. So our 12 grams of O2, how do I continue this one? Bring down grams O2. Do I do anything with 12? No. Okay. And what do I want to get my grams O2 to? Moles O2. And who can tell me why that is? Why do I need to get my oxygen into moles? Yeah, exactly. So I think you're kind of floating around the idea. You cannot go grams of one to grams of another. You can't go grams of A to grams of B. I can't go grams of water from grams of oxygen. You can't do it. The only way you can change chemicals is with a mole-mole. So the only time you should ever see 2 different chemicals is if they're mole-mole. Does that make sense? A handful of you on the first mini quiz had grams of one to moles of another, or moles of one to grams of another. You can't do that. There's no shortcuts. You have to get your grams of A, in this case oxygen, to moles of oxygen, then use the mole ratio to change chemicals to water. Okay? So, how do I get this number? Where does this come from?
Now you're figuring out the total grams that O2 is, and that's 32.
Right.
You use
Exactly.
the periodic table.
From the periodic table. So we have a molar mass, grams a mole, and it's from the periodic table. 1 mole of O2 is 32 grams of oxygen. Again, this gram, mole, gram always comes from the periodic table. Kind of neat. Also fun, your mole will always be 1 when it's a gram to mole. Always. Okay. Some people like to pull the 2 or the 3 from the balanced chemical equation. That's not where you use it. It's always gram per 1 mole. I fixed it on a lot of people's worksheets, but some of you still got it wrong in the quiz. There's a reason we do the worksheets. When I fix the answers on the worksheet, please figure out what you did wrong. Even if you get a 3 points, still look at what you did wrong so you can get it right on the test. Okay. So we're done with this block. Now let's look at hydrogen. What do I do with the hydrogen? Yep. Grams H2, 2 moles H2. Good. And where do I get this? Periodic table again. 1 mole of O2 or H2 is 2. Pretend that's a 2. 2 grams H2. There we go. 2 grams H2. All right. First box done. Check. Now we're at moles O2. What do I need to do now?
Moles O2
Bring down moles O2, and now that I have moles, I can convert to the unit I want, which is moles of H2O. Excellent. Similarly, with the hydrogen, I got my moles of hydrogen, and now I convert to moles H2O. What do I need to figure out now? I got to do the balanced chemical equation. So I know that if I have H2 and I react it with O2 in a big kaboom, I'm going to make H2O. So there's my balanced chemical reaction, right?
No.
No, not balanced. How do I balance it?
Put a 2 in front of
Put a 2 in front of the H2, 2 in front of the H2O. 2 by 2 is 4, 2 by 2 is 4, 1 by 2 is 2, 2 by 1 is 2, and now it's balanced. And now that it's balanced, I have the numbers that can go into the mole ratio. What number should I put in front of the mole H2O? 2. How did you come up with 2? Exactly, the 2 up there. What number should I put in front of the O2? 1. How did you come up with 1? Technically a 1 right there. It's an invisible 1. What number here? 2. For the same reason? What number here? 2, because there's a 2 in front of the H2. Cool. So mole ratio done. And let's stop right there.
The only thing that like messes me up is the equation that you have to write.
The balancing?
Yeah.
Well, the good news is I will always give you the equation, but you might have to dig back for the last couple of units and balance it yourself.
Yeah, no. Okay, so you always will give us the equation. Oh, okay.
I will always give you the equation. I may not always balance it for you. Okay, so there you go. All right, cool. So we're 1 step away. What's my next step with moles H2O?
Move it down.
Bring it down.
Bring it down, moles H2O, and now we're going to go to grams H2O. Same thing here. Moles H2O and grams H2O. When you are doing a limiting reactant exercise, the last box will always be the same in both T-charts. It will be the same in both T-charts. It's because you're going to end with the same grams H2O. So 1 mole of H2O, 1 mole of H2O. How many grams is 1 mole of H2O? 18? How do we come up with 18? Periodic table. 2 for the hydrogens, 16 for the oxygens, and we have our grams H2O, which is what we're looking for, and now we can do the math, and we can find out which one is limiting. 12 by 2 by 18 divided by 32. 32 one gives us the lower number, that's going to be the limiting reactant T-chart.
Is it always the lowest number?
Always the lowest. Always, always, always. It's my 18 cookies versus your 24 cookies. I'm sorry? Uh-huh. Yay. I think somebody stepped on it, but I tried to straighten out the thing a little bit without, I don't want to break it. But if you want pliers, I have pliers. Mystery solved. Okay, so if oxygen was the limiting reactant, how much water would we make?
13.5.
13.5 grams of oxygen. Okay. And if hydrogen was the limiting reactant, how much would we make?
45 grams.
45 grams of water. So which one's the limiting reactant? Oxygen. Oxygen's the limiting reactant. So this first T-chart is the T-chart for the limiting reactant. Understand, when you have two reactants, I'm going to be looking for both T-charts. If you flip a coin and happen to get lucky, you're not going to get all your points. Okay? If you're given two reactants, you need to do two T-charts. Okay? Give me a thumbs up if we're ready to move on.
Yes.
Okay, any questions? Let's do it again. One more, second verse, just like the first. If 35 grams of sodium react with 55 grams of chlorine, how much sodium chloride would we produce? Let's find out.
Can we start with the balanced equation?
You want to start with the balance? That is perfectly fine. So if we had Na and we added to Cl, then we're going to make NaCl. All right.
Yeah.
Do we balance that guy? Yeah. 35 grams of sodium. And 55 grams of chlorine. Is our equation balanced as it is? No. So we go. How would you balance it?
2 and 5.
2, 1, 2. 2, 1, 2. All right, sounds good. Two sodiums, two chlorines, and we're off and running. Do you need me to help you on this one, or do you think you can give it a try on your own? Try on your own. Okay. On your own, you shall try. I'll be a couple minutes behind you. small classes can handle it. And it's a huge mess if we spill. It's a really fun lab. Learn some really handy skills. Our mid goal will always be to get our first chemical into moles so we can switch over to the maybe turn that chemical down to moles. This one's really close. They're only different by a couple grams.
I hate that sometimes my rounding's a little bit different.
Yeah.
In this case, even if your rounding is different, one will still be larger than the other one.
Yeah.
The hardest thing about limiting reaction exercises is reading the exercise to know that they gave you 2 reactants. When they give you 2 reactants, then you have to do a limiting reactant exercise. I mentioned on the little blue chart too. Okay, without answering, who thinks they got it done? Okay, cool. Looks like 1 or 2 more people need about a minute. And again, your correct answer is you don't be off by, or you don't be different by 1 or 2 grams. They're really close. Okay. If sodium was the limiting reactant, how much sodium chloride would we make?
88.26.
About 88 grams?
Yeah.
Sounds good. And if chlorine was the limiting reactant, how much sodium chloride would we make?
89.859.
About 90? Yeah. So they're really close, but the sodium is going to run out first. So the sodium chloride is, or the sodium is our limiting reactant, and it's only going to allow us to make 88 grams of sodium chloride. So the sodium runs out first. Sodium is the limiting reactant. Chlorine is the excess reactant. Okay. Give me a thumbs up if what we're doing so far makes sense to you.
It makes sense, but I didn't round like you, so I got like 92 for the first one and then 91 for the second one.
92.
Yeah.
That
I did 35 times 2 times
rounded up on one and down on the other?
I get it.
The good news is when you encounter it on a test, it's going to be really obvious. They won't be very close to each other. So yeah, you should have rounded up on the other one where you rounded down and down on the one you rounded up. But oh well.
I thought it would be like
I thought it was
grams
something-
of Na, and then the bottom is the grams of Cl2, not
No.
the total.
In a limiting reactant exercise, you don't compare one to the other. You compare one to the product, the other to the product. Two separate exercises. Now, there are times where you want to go reactant to reactant, but we're not going to learn those because those are confusing. Okay? Are you ready for one more? Okay, this other one is a special type of limiting reactant exercise where it doesn't ask you for a product. All it wants to know is which one is limiting. So in this exercise, 177 grams of HNO3 react with 95 grams of Fe. Will all the Fe be consumed? It doesn't care about how much we make. All it wants to know is which one is limiting. And I'll show you how to do that. It's not any more complicated. It's actually easier than the rest of them. Can I erase the water?
Yeah.
Okay. All right. So the reaction is this. It is iron reacting with HNO3 to produce hydrogen gas and FeNO3 twice. That's our reaction. Just like it's hydrochloric acid, just like we use hydrochloric acid with zinc, this is using iron nitric acid. Both ways, we're going to make hydrogen gas. So our first reactant is 177 grams of iron. And our second reactant,
That was 95.
like I said, 177 grams of HNO3. And our second reactant is 95 grams of iron. Oh, poor dry erase markers can't keep up with us. We need heavy duty dry erase markers. So go ahead and get this one started. Then it looks like most of you have hit a certain point, then we'll move on. Now, if you got to this point, to the mole ratio, the question becomes, Mr. Byers, it doesn't ask me for the product. Which product do I use? Doesn't matter. Pick one. Because regardless of what product you use, the limiting reactant will make the least. So what product do you want to use? H2. That would be the simplest thing. H2, rather than doing all the math for iron 2 nitrate, let's just use H2. And the reason we're using H2 in both cases is it doesn't matter what product we choose, as long as we choose the same product. All it's asking ultimately is which one is the limiting reactant. If iron is the limiting reactant, it will all get consumed. If HNO3 is the limiting reactant, not all the iron will be consumed. Does that conceptually make sense? Yes. Okay, cool. So go ahead and finish this one out, and we'll find out which one is the limiting reactant. because I want to remind you every chance you get, how many things go in each box?
3.
3 things go in each box. Do not use shortcuts in stoichiometry. Shortcuts are the way to ruin. Don't use shortcuts. We're going to do a practice exercise just like before. Practice exercise all day tomorrow on limiting reactants. And then, worksheet, yeah. And then on Thursday, we like have that lab I mentioned, which I'm looking forward to because I haven't done it in like 5 or 6 years.
When Mr. Byard is excited about it.
Yeah, labs are fun. I think you're going to enjoy it too. And it's really, it is dense with learning. But when someone spills, it makes a huge mess. So I haven't done it in a while. I'm going to give it a try this year.
Because we're a small class.
All of my classes are small. Okay, so the answer to the question: will all the iron be consumed?
No.
Okay, so it sounds like most of you are saying no. What proof do you have that it is no?
That's 2.8 grams of H2. The other one is 3.4 grams of H2.
Good. Excellent, excellent, excellent. Yeah. So, 2.8 grams of H2, not He. 2.8 grams of H2. Obviously, this gives us our limiting reactant. So our limiting reactant is the HNO3, the nitric acid. So that means that nitric acid is going to get used up first, and there will still be some iron hanging around. So no, not iron. All the iron will get used up. Okay? Give me a thumbs up if this makes sense. Okay, that's about it as exotic as limiting reactant gets. Okay. Any questions? Okay, if there are no more questions, then you may use the remainder of class to finish up your lab.